today about the age of the Ursa major moving group. So we've already heard a little bit about moving groups today, but I will be talking about one of the most nearby, one of the nearest moving groups. So I was looking at the program for today, and I noticed Cassie's talk coming up, searching for companions around cool stars, and Travis is going to be talking about hunting for AGN outflows, and I'm talking about the age of the Ursa major moving group, and I realized that my talk wasn't quite at the same level. I was missing something. Then it hit me. Cassie's searching, Travis is hunting, and so I'm changing the title of my talk to Keeping an Eye Out for the Age of the Ursa major moving group. All right, so first things first, what is a moving group? Well, the kind of moving group that the Ursa major moving group is it is a cluster that is dissolving. So first let's look at a nice video of a cluster forming. So the size scale, or the mass of this cluster that's going to form this molecular cloud is 500 solar masses, 500 times the mass of the sun, and the size is about 1 light year across. And you've got the red is sort of less dense material, yellow is more dense material, and you've got these stars that are forming, as you would expect with a cluster that's collapsing, and what I've already told you. So some of these stars you'll notice are going to fly away. That's a natural byproduct of birth. You get some thrown out, and most of them will stay in the cluster, nice and clustered. And this whole process, or at least the length of this video, is 200,000 years, more or less, which is a long time on human scale, but it's a very, very short time, astronomically speaking. Anything less than a few million years is a very short time. So here's our nice newborn cluster. Get a nice 3D view of it. Oh, also to credit Matthew Bate at Exeter did this. I just stole it off YouTube. Anyway, so you got a cluster forms, and then that cluster goes around the galaxy. So GC here is galactic center, and then this is just the distance scale that's appropriate for that. This circle of stars at the beginning of the GIF, that is just a whole bunch of stars in the solar neighborhood, and based on their velocities, this is sort of a projection of where they will be as we orbit the galaxy. And this orbit takes about 250 million years, or 250 million years. And the important thing to note here is that even if you've got a cluster, which is going to be a much smaller circle here, you're still going to be spreading out. So this is sort of how a cluster dissolves into a moving group. That's the best way to think about it, is all these stars have their own unique orbits. They're slightly different. Only slightly, though, and so that makes them spread out over the course of 250 million years. So that brings me to the Ursa major moving group specifically. These 15 stars that I've got boxed are the nuclear members of the moving group. So you've got nuclear members, and then you've got the stream that we just heard a lot about streams. I don't care about the stream so much. I care more about the nucleus. Those are the ones that are most well known that they are from the same cluster. The stream stars, it's a bit trickier, but these guys, we're fairly confident that they're all from the same original cluster. They all formed at the same time. The white boxes are looking at A-type stars, which I'll talk more about A-type stars in a second. Those are the ones that I care about, and then the red boxes are ones I don't care about. Right, so some fun facts about this moving group. It's 25 parsecs away, making it either the nearest or the second nearest, or it's very close is what's important there. There are about 62 stars in it, 15 are in the nucleus, and then So some observant people who like to count things may notice there's only 13 boxes. 2 of the boxes encompass binary stars, so there's your 15. Previous age estimates are 300 million years from these guys and 500 million years from these guys. Another fun thing to point out, there are 2 stars here. Ancient peoples would use this star, Alcor and Mizar, to test the eyesight of their people to see if they could be the archers in the army. So if you can see these 2 stars as 2 stars, you've got good eyesight. I can see them as 1 star. Well, from here I can see them as 2 stars, but in real life I see them as 1 star. My eyesight is not great. Anyway, so Alcor and Mizar are fun because Mizar, the bigger one here, is actually a binary star. It's a spectroscopic binary, and then Alcor is also a binary, but its secondary companion is much fainter. It turns out that I don't care as much about Mizar because the fact that it's a binary makes it complicated, and I don't like complicated things. So I've not actually observed it. There are actually good reasons besides I don't like it, just so you know. So here are A stars. This is a Hertzsprung-Russell diagram, abbreviated to HR diagram. You've got brightness on the y-axis and temperature on the x-axis. Most stars in the universe are these silly little M dwarfs. And then you've got the rest of the main sequence here getting fewer and fewer as you get to higher and higher mass. Just the way that the mass is distributed itself across the universe. Most of it is in smaller stars, and then fewer and fewer as you get bigger. The sun is here. It's a D-type star, and these are the A stars. Specifically, I care most about these. There are 234 A stars within 50 parsecs. 127 of those, or about 54%, have observed rotation speeds of 100 kilometers per second, which is fast. And there's probably more because you see here this is called V sine I. V is the rotation speed, and then I is the inclination. So it is likely that many stars with low inclination, so they're pointed sort of pull on, they're spinning around this way, and we're looking at them this way, then we'll see a low V sine I, even though they are rapidly rotating. And some of those have been observed, including Vega, which is sort of the standard star for the magnitude system. It is 0 magnitude, and it has been 0 magnitude for, I think now it's not actually 0 anymore, but neither here nor there. It turns out Vega is one of these pull-on rapid rotators, and it's very cool. So you see this rapid rotation in all stars that are more massive than about F2 class because they don't have strong global magnetic field. So all stars, when they start off, when they form, they collapse from that giant cloud, and they're going to be rotating very fast. And then you've got this disk of material, the leftovers of that process, and if a star has a magnetic field, a nice strong global magnetic field like most stars do, then that magnetic field will interact with the disk and slow down. A stars and likewise O and B stars do not have those global magnetic fields for reasons I won't get into here, and so they don't slow down. They stay rapidly rotating to the point where they are measurably larger at the equator than they are at the poles, which I think is fun. So why A stars? Why do we care about A stars? So here is a modified version of the HR diagram where instead of brightness we're looking at size, so radius versus temperature, and what I've got plotted here are the mass tracks, evolutionary mass tracks for 4 stars of 4 different masses ranging from 1 solar mass to 2.5 solar masses. So what we're seeing here is this is how a star will change in size and temperature as it gets older. And the red circles, the bottom of the red circles is sort of its 0 age, and then the other red circle is 500 million years later. I chose 500 million years because that's the age of the moving group I care about. And so these three here are sort of the range of masses that A stars have, and then this is one solar mass, so the mass of the sun. So it will change very, very little over the course of 500 million years. But A stars change size and temperature drastically in that same amount of time. So you can really use those to determine the age of the star. Is there something else I wanted to say there? I don't think so. All right, so yes, there was. So temperature is difficult to determine directly. Luminosity, though, brightness is very easy. And if you know the brightness and the radius, then you can get a temperature to put the star on this diagram and compare it to the models. So finding a radius is what I do, basically. And to do that, I use the CHAR array on Mount Wilson. It is an interferometer, which means it interferes the light from multiple telescopes to simulate a much larger telescope. So here's a nice cartoon of it with you've got 6 1-meter class telescopes in this Y configuration, and you've got these big tubes of vacuum where you shoot the light through. So you collect light at the telescope and then you shoot it down to this beam combining lab, and you interfere the light because light's a wave, it interferes. And based on the way it interferes, you can measure a size of a star along a given angle. A side note here, the 100-inch telescope is the one that Hubble used to basically make him famous in the astronomical community, and he got himself a space telescope named after him. So this is a very historic observatory that we've got our stuff around. So you simulate a telescope that is about this size. So this is 300 meters at the longest baseline, and you can simulate a telescope that the resolution of a telescope that big. You are limited in brightness, so we have to look at very bright stars, but that's okay because we're measuring them with very, very high resolution. And I typically will use 3 telescopes. And so basically I'll get the size of the star I'm looking at along these 3 orientations. And if it's a nice spherical star, then those will all be the same. So here I've got a model of a nice spherical star, and you see that these sizes here that I've measured are not all the same. This is longer than the nice spherical star. This fits nicely, but this is a bit shorter, and it just doesn't work. But as I mentioned earlier, the A stars tend to rotate very rapidly to the point where they are significantly oblate, so they are wider at the equator than at the poles, and when I take that into account, it fits nicely. So that's a bit more complicated than just looking at the size of it. And so now I've got 5 different parameters that I adjust. I've got the size, the rotational velocity of the star, the inclination of the star, the temperature of the star, and the position angle. And we'll go over those real quick. So here's comparison of 2 different size stars. Duh, one's bigger. Come on. Next, two stars of different velocities. So nice spherical, and this doesn't look right. Maybe it's the angle. Does this look oblique to you guys? Okay. Okay, I'm seeing it at a weird angle then. All right, so that's what happens when you speed it up. This is what happens when you change the inclination. So all these points are just points of longitude and latitude. And so when you angle it down by 60 degrees, you've got the pole there instead of at the top. Wait, no, that's not 60 degrees, that's 30 degrees. My bad. Then you've got position angle, so just turning it sideways by 45 degrees. And then finally, temperature. So temperature doesn't actually affect the shape of the star. What it does is it affects the brightness of it, for lack of a better term. So we get that from, for each of these points, I measure, or I calculate a temperature, and then based on the temperature of those points and then various models, I compute a spectral energy distribution of the star, so how bright the star is at various wavelengths, and then take measured photometry, that's the red point, so people have measured how bright the star is at these various colors, and the model shows the blue squares, and they're in pretty good agreement, so that's good. So use temperature to sort of fit this. And I do all that simultaneously. And in the end, for the 6 stars that I observed, I get the size and temperature plotted here. So remember that the second red dot here was 500 million years, and these two, yeah, that looks like it falls right around 500 million years. These guys, 500 million years is up here. That doesn't look right. But 2 things to take into account. From here to here is 400 million years. So this bit of stellar evolution goes by very quickly. So this is 400 million years, so that's getting closer. And then on top of that, because they are rapidly rotating, they evolve slightly differently. And when you actually take that into account with the models, this is about right. So this is what you end up getting, plotting here the mass of the star versus the age. And so these 6 stars, 2 slowly rotating stars, and then 4 rapidly rotating stars. And you find that they're all about the same age at about 500, and the sort of lined region there, that is what the previous estimate found of 500 plus or minus 100 million years. So yay, with my 6 stars, I was able to reproduce the work of 60-something stars. So that is good. That is promising. And really, what I'm using this for is a way to test just this whole method that I described for analyzing rapid rotators and analyzing the age of A stars, to be able to do that for stars out in the field, for stars that are not associated with a cluster or with other stars of the same age. For just field stars, being able to figure out their age is very difficult, and so by testing this method on a cluster of a known age and finding good agreement, that gives me confidence that I can actually do that for field stars. So in summary, stars form in clusters. Clusters evolve into moving groups. Stars get larger as they age. A stars do this much faster than lower mass stars. Not quite as fast as higher mass stars, but there are a lot fewer of them. We can do this. We can measure the size of the stars using interferometers like the CHAR array. We can learn a star's age from its size, especially for ones that evolve very quickly, like A stars. And the A stars in the Ursa major moving group are 500 million years old. Are there any questions? Yeah. So they're all related, and that is why it's not just the size you care about, it's also the size and the temperature. So, for example, a star that's this temperature, but this size. So temperature and size are related in the way that mass and age are related. So you've got a star here that is 2 solar masses and 0 years old, and it's got this size and this temperature. And so basically you compare any star you want, the size and temperature, to the models to get a mass and an age. So it's related, but you do need to know 2 of luminosity, radius, and temperature. You need to know 2 of those things, because you could get the third one if you know 2 of them. That's about 100 kilometers per second. That's why I use that as a, that's why I said that that's what was rapidly rotating. Here, that's about where you start to see that. Hours? Well, more like 8 hours-ish, I think. No, it's a month. Sun's a month. Yeah, Jupiter is 8 hours, but it's also a lot smaller. Mm-hmm. Yeah. Yes. Yes, that's exactly what I do for the nice spherical stars that are slowly rotating. For the oblate ones, it's a little bit more involved. But yes, that is exactly what you do for spherical stars. Yeah. This one? Wait, which one? This one or this one? Because there are two that are outside the range. The younger one? Okay, so that is a star called Alioth, and I'm not entirely confident on the data on that one. It's not the best quality data, so I think that's a part of it. And also just the models. So part of this is to test the limits of the model. So it's not too much of an outlier. I don't know if that answers your question. Yeah, it's Alioth. Okay, what was the question? Yeah. Sorry. Right down here. No idea. This is actually, so I use this more as demonstration than anything factual. This is actually a reversed form of the GIF. Basically, what the original study did was sort of look back at the stars in the local neighborhood to see where they were one orbit ago and then project it to now. And so I just use it as a demonstration for how stars spread out with their orbit. Okay. Yeah, it's just, okay, so I was just saying it's just because it's an elliptical orbit. Hello.